Okay, Gesa already gave introduction into the physics, so today I will not talk about the physics, only about the GPU aspect of it. But first a bit where I'm from. I'm from the forest, like the institute Gesa is from, also outside of city in the forest. It's a Helmholtz Research Center outside of Dresden. My background is in statistical physics and theoretical solid state physics. So last year I talked about actual statistical physics. Now I will only talk about the GPU. So first I will give you a short introduction into the connection between this, these random graphs and the GPU and what you need to know. Then talk about the implementation in detail. It's basically focusing on a certain aspect of the implementation of the optimization of such problems that you can take home with you also for other problems, I hope. And then talk about the, some numbers about the performance of what we got there. So I have one equation in my talk, or basically also many equations, because I will always repeat this equation that Gesa already showed you. And it describes this network of coupled oscillators. And for this description, it uses a system of ordinary differential equation. This is such a system, and basically it describes the time change of the oscillators at a certain time, at each position with time, and this is the change over time, basically. And so we do a time integration to get the evolution of this whole thing over time. First, I would like to talk about some things we didn't implement. For one, it's the ODE solver, because people already did this in quite nice ways. It is this library, part of the Boost numeric library, which is called ODE-int, which implements a number of ODE solvers, ranging from Euler, going over Overcoat, fourth order, many orders basically also, and until things like Boulier-Ströer and such things, and implements different steppers, symplectic steppers, adaptive steppers, and everything. So this Boost numeric supports a number of backends to actually do the computation. So it's a template library which just takes the backend where the computation is to be done as a template argument. One options there, for example, is thrust, which is kind of like a parallel SDL, which we were talking about yesterday, which only works on CUDA, unfortunately. And there's also, for example, vecCL, which is kind of also a vector operations library, which has, again, different backends, and two of those are the important ones are CUDA and OpenCL. Although in our case, we only used, in the end, we only used NVIDIA GPUs. vecCL is this library for offloading. And it does also directly support custom kernels, so kind of within the language or the whole pattern of using vecCL as an abstraction for the device, you can also directly pass the device, custom kernel to the device, like writing a CUDA kernel, just without using CUDA-C, but just having the kernel and passing it through the vecCL API, which makes it a bit nice to have the vectors and the custom parts kind of in the same shape. Yeah. Gesa already said this thing about the fourth order Runge-Kutta. The thing that we need to do, or that is the also time-consuming part of the whole thing, is actually computing the derivatives in our equation. I just want to show you, for example, the thing is, the Runge-Kutta, what the Runge-Kutta is basically doing is basically summing up these derivatives here over time in order and multiplying them by the time step in a smart way in this case. Calculating the derivatives is much more work, because for each of these numbers, because we get one number per oscillator, we need to sum up multiple numbers actually and compute the sine function and such things. So this is why this kind of consumes like 99% of all the GPU time. Short side remark about this vecCL thing. In terms of vector library, which is kind of how Boost Compute is using it, because it's kind of just doing these vector operations to implement all these solvers, what you can do with it is basically, so you have data on your host, which you can, for example, have as a STD vector. And then you have this vex vector, also a template, which is then the representation of a certain device, of the data on the device. You pass, when you created a context, that's the device context, which also contains the information about which backend it actually is. So at the first, you create a backend context from your backend, basically, from your deployed devices. And in this constructor called also directly copies in the host data. And then basically it has overloaded operators, for example, here times equal, so we can square it in place, for example. And then we get the result and we can just copy it down if we want to. So looks principle like this. Some downside there are that it's kind of using it's kind of a pseudo single source version of dealing with GPU code. So it's pseudo single source because it looks like you put things in a single source, but then these expression templates that are used here are kind of expanded in the end into strings which are compiled at runtime using either the OpenCL API or using the CUDA driver API, or compiled using MVCC, but then it's submitted via CUDA driver API. And so because of this, you don't really have function templates when you're talking about your custom functions, at least. So when you want to have kind of a template function, which is a custom thing, then you need to use a custom kernel, which directly means writing a kernel. And then you inject strings to actually get your kind of, for example, a predicate in, which describes your model if you want to do something in generically. Which is why the thing which I will talk about, in the computation of the derivatives, will be implemented as a custom kernel instead of a custom function, or because of optimization reasons, it can't be implemented using the normal vector language that you have. Okay, so now back to our equation. First, a short primer on the types of networks we could do this thing on, because this is what the parallel implementation depends on. First, the two ways which are actually the regular networks, like a fully connected graph, which kind of makes it an n-squared problem. You can easily vectorize this. It's pretty straightforward. In this case, you could use the vector API if you want to do that. Then you can have a regular lattice, which is equivalent to a band matrix, because kind of the band matrix would be your adjacency matrix for your regular lattice, for example. In this case, you can do a stencil integration, and in both cases, you do not need to explicitly store the network topology. You might need to store weights connecting between two, but you know who's the neighbor of whom, because everyone is somehow regularly neighbored or paired up. The thing we are looking at here are sparse random graphs. They become a bit more complicated. I changed the equation a bit, because now we are not summing up over our adjacency matrix, but we already optimize a bit and work with neighbor lists, basically, because we need, for each lattice site, the set of neighbors is basically random somewhere, so we need a list of those. And network, that's what you also saw from Gesa. So you have this network which is irregular. It has parts like this moduli which are kind of densely interconnected, densely interconnected nodes in the network. There are nodes which are not highly connected with other nodes and such things in this type of network, for example. So we need to explicitly store the network in neighbor lists. And it kind of gives us a sparse representation of the network topology. And these sums over the contributions we get for a certain node from its neighbors, when we have the incoming links in our network, these sums are basically the sums of random values in our memory, which are scattered throughout. And for this is basically where then the take home message comes in. For this, we need some techniques to use SM to kind of make this one more appropriate for SIMT vectorization, sort our memory especially, and also to have memory accesses as good as can be. And also at the same time to the operation ordering so that we reduce load balancing. That's directly the next step. I want to give you first a short primer about the GPU architecture. You heard a lot about this. I just want to give you a small focus on what is relevant in this talk. So basically the whole architecture is the whole GPU is like a multi-core vector processor. Each core is a vector processor, so you have this, these blocks, they are more like the CPU threads actually running on one of these multiprocessors. And then you have this SIMT concept, single instruction multiple thread, which is similar to single instruction multiple data, where you have one of these things which the GPU calls threads, or CUDA calls threads at least, running on one of these multiprocessors and executing vector instructions there. These are all running in lockstep. And ideally, you also have your memory transactions vectorized. So which basically means any transaction you have should be continuous among the addresses which the threads are accessing, or at least all of the threads should fall into the same, like about 64-byte boundary range, with some details depending on the architecture whether that needs to be aligned or not. But the important thing is basically coalescing everything else. In today's GPUs is mostly caught by caches. If you have misaligned access, then at least if you read somehow sequentially, then your misaligned access will basically be compensated by some other part of the memory already being cached after this misaligned access, and the next misaligned access will already be half cached. So it doesn't cost you so much anymore on modern GPUs. And basically this is, I already mentioned, not so far from the CPU. It is often just ignored on the CPU, because on the CPU it's not like if you don't do this, you don't get any performance out of the device. And the GPU is, if you ignore this, you can basically be screwed. So the SIMT is basically SIMD, and except that it's a bit nicer to program, or much nicer to program than on a CPU. And these vector transactions you need is basically also like cache lines. Cache lines on a GPU are also then a bit longer and a bit similar. Main difference here is GPUs, except for the programming model, GPUs have much wider vectors. As I said, these 64-byte. Ideally, you have all of this, like 32 threads actually running in lockstep without divergence and all accessing data in a neat way. So we're talking about a vector processor, so we want to vectorize. And so we first look at our equation that we want to compute. And so decide what we want to vectorize about. There are basically two loops implicit here. One loop is explicit, which is the loop over the neighbors of each node. Something you can compute these values in parallel, but the problem is each of the nodes doesn't have so many neighbors. The network that Gesa was talking about, the brain network, has about 50 links per node, 50 incoming links per node on average. But we will see later that there's also a large spread in this number. So there can be some which have 1, some which have 3,000. But even though 3,000 doesn't give you lots of parallelization opportunity, and 1 especially doesn't. So this loop is too small to be parallelized efficiently. So basically the implicit loop here, because we need to do this for all of our nodes, all of our oscillators in our network. So we parallelize over these. We can vectorize this. All of these sums are independent. They just access different memory for reading. Sometimes the same memory for reading, which is actually good because this gives us cache effects. And also, we don't need to, because we don't parallelize a sum, we don't need to do a reduction afterwards, because we sum up the sum sequentially. Let's talk about where our data comes from. We have 3 different types of memory accesses here, basically, except for the final write, which is on the left-hand side here, where we store the actual derivative in memory to then have it used by our solver. First, we can have our eigenfrequency of the current oscillator, which is obviously a local value. We can easily sort this. We know where we parallelize, where it is. Then we have the sum over our neighbors, all of the weights we need to multiply, and we need to figure out where the neighbors are. So there's a memory access here where we need to access the memory where the index of the neighboring site is stored. And then, we have this local access again, which is just our local phase. It's always the same for the whole sum. We can even just store it in register. And then we have this remote thing, that is the phase of the other oscillator, and this one is just completely random, basically, because we have a random graph Or we have a hierarchical graph with moduli. In this case, it is not completely random. They are a bit grouped, but a priori they are random. We can't tell where it is, what is happening with it. But first, the good news, this thing obviously doesn't contain any branches, except for the fact that this loop has a different length, or the sum has a different number of elements, or the loop has a different length for each of our oscillators. But apart from this, there are no branches, so there's no diversion. We can vectorize this expression. Downsides are no predictable data reuse. So we can't even use shared memory effectively. But if we have kind of random data reuse, caches can help. Modern GPUs do have lots of caches. They, as I mentioned, they actually are pretty forgiving in this regard. And main downside is also there's actually a low computational density because we are just streaming the data. We need lots of data to actually do just a small amount of computation on it. Even though there's a transcendental function in here, it's not really enough compared to the amount of data we need to actually compute it. So the things we can do and we need to look out for to have a nice implementation in the end is to maximize the memory locality of the reads where we can. And this is especially this orange part here, this is the neighbor sum, because this one we can order, and this is the one that also leads to the to load imbalances, and we can try to minimize these kind of at the same time by looking at how we order our data. In regards to the red part, we can't do anything about this. This is random. We can hope for cache effects in this sense only. So let's focus now on this part. How do we store our neighbor lists? They are not shouldn't be in a if label list because then we would be also accessing randomly. What we do is basically we don't store neighbor lists together, like not the list for one node in one place and the list for another node in another place, but we merge all of them and so that we can kind of align it with our parallelization approach or with our vectorization direction or dimension along which we vectorize. So in this case here, for example, we have our list of all the first links of our node. So we look at of each node basically. So we want to have a network with 10 nodes, at least 10 nodes which have at least one link. So we store all of our first links continuously. So when we vectorize over all of our nodes, all our 10 threads in this example are able to access this one as one long vector basically, and we have a really nice access to, for one, the index, the index of our neighbor, which then leads to the other remote access, random access, and then we also can, in the same way we also store, of course, our weights, which belong to these links, same layout. Okay, then we have the second link, which is now going up in our sum here. We go to the next neighbor here in our sum. And again, now we have the list of all our second links. And as you see here, the first 7 threads are accessing this. And the others don't have any second links. They don't do anything anymore. They are basically done and so on. And you have something like this. What you can already see here is that it's sorted. The node with index 0 is the node with the most links. The node with the highest index is the one with the least links. This is what reduces load imbalances, because when you submit this whole thing to a GPU, I skipped one part because just want to illustrate this. That's basically how the memory then looks like, because you have linear memory and any memory basically. So this is what it looks like, and this prefix sum here is just giving you, where the different sections start. So finding things. If you don't iterate, actually, it's kind of hard to find things in there. But when you want to do the iteration, it is pretty straightforward and efficient. And now what's the load imbalances? If you think, for example, about a GPU, imagine a GPU which has a warp size of 2 threads. Then you would see, okay, for these 10 threads running, or 5 warps running, 5 warps have work. Then you go to the next one, and you see only 4 warps need to do work. The last warp already finishes iteration. Since all the threads in this warp are running lockstep, this one still needs to run, even though this one can't free any resources. But this one is already gone, and could, for example, allow another warp to be scheduled, which has even more one link nodes to add up. basically. And the way the scheduling on GPU works also kind of ensures that this is 0. 0 started first. If this is the one that has 3,000 links, for example, in the connectome example, this one will be started first and will probably run until all the other ones are finished too, basically, adding up all the one nodes. This is how you maximize occupancy, even though you still don't guarantee that you have perfect load balance, but that's the cost of randomness. Okay, so let's see how this actually performs. For this, we can compare two examples, just of curiosity. The blue one is the graph, is a histogram for the number of links, connected or incoming links to each node. We need to sum up for this connectome graph that Gesa presented. About 800,000 nodes and 40 million, because it's average degree of 51, about 40 million links. Actually, 40 million are the number of directed links, the number of incoming links. Since we symmetrize this in the simulations, we store these neighbor lists, so we basically double this, because we need to store the backlink explicitly. So effectively, we have like 80 million links, which we actually need to sum up in the end. And you can see this distribution. You have quite a number of nodes which actually don't have many links at all. 1 to 10, not so much. And then there's a long tail. There are things which have more than 3,000 links. And then we can compare it with an actual random graph. Random graph means we just choose random pairs to connect, pairs of nodes we connect. The same number of nodes, and we choose just so many links that we have the same average degree, the same number of links, 80 million links basically, completely random. Of course, you kind of get a bell curve for this histogram in this case. So you could think that this one, actually the red one, looks a bit more friendly, because load balancing, not so bad, because you actually have you have this pretty narrow distribution of numbers of nodes which you have, so you don't have some warps waiting for others for 3,000 steps in your sum. This is the performance of this. Again, the blue one is the connectome and the red one is the random graph. And this is the number on CPU. I have to explain a bit about this because we only have a single-threaded implementation for the CPU, but comparing GPU to single threads doesn't really make a lot of sense. So what this number is actually is kind of like an effective time per iteration if you consider the throughput you can get on the CPU by running multiple simulations at the same time. We want to average over many runs, so that's it's legit to do to get load on the CPU. But this 12-core CPU running 24 simulations at the same time, so it's oversubscribed. It can hide some latencies from the memory accesses because it also suffers from random access. And so we see these times like about 1 second for each update on the brain connectome. We also tried to just take this connectome, this sequential code, put an OpenMP pragmas that doesn't give really good values. It is a speed up compared to the sequential code, but it's not really efficient. The brute force version here is more efficient, as you can see. So that's what we will compare to the GPU. And then we have low tier GPUs, current Pascal generation, and server GPUs P100 and V100. And you can see the server GPU compared to the V100 is about a factor of 20 speed up. But the interesting thing is that in this case, it's usually the random graph that is a bit slower than the brain connectome. Because, well, in this case, you don't suffer from load imbalances because it's sequential. So the downside of the connectome doesn't really play into it, and the random graph is just completely random. We can throw caches out of the window, while the connectome has these moduli which are kind of locally connected. So even though the CPU code isn't really optimized, it can still work well on this, and you also see a similar effect here. But in this case, you can see that the load imbalance, because of our sorting of the memory, doesn't play so much of a role. The more important thing is the complete randomness of the random graph, which kind of, in this case, kills the performance. And how does it kill the performance? That's because of low load efficiency. So this is the right, this is 100% efficient, as I said, because it's just a vector operation, basically. Here we have the inefficient loads. This is basically efficient because we do have this continuous memory, we have it sorted and everything is neatly in lockstep. But this part is random and the overall global load efficiency is about 47%, which considering this is basically a sign that we were able to actually sort out these parts and only suffer from this one part, which kind of reduces the performance there. The thing is, we only saturate the gross load, the bandwidth, memory bandwidth of the device to about 70%. So it means that the gross load thing, so basically we kind of request 160 gigabytes per second on a V100 here. Since we only have 47% load efficiency, it means we actually need to transfer 320 gigabytes of data per second. But still, this doesn't saturate the bandwidth. So we're not actually bandwidth bound, even though we are inefficient with this. The main problem is, in terms of performance, is the data request for data, the reads, especially this reads, if the profile doesn't tell you this, are the ones we always wait for this. 50% of the time, when a thread is waiting, it is waiting because it is waiting for this value, which is coming from somewhere. So basically, this memory latency, the code is memory latency bound. Higher occupancy could put a dent into this, but also not really much because we already have 3/4 occupancy. So, and we can't really reduce the number of registers found out because apparently the sign function gobbles up lots of registers, so we are not optimal in this case, at this point. So to the summary. So we do have an efficient implementation for this integration on random graph, which is about 20% more performance than a equivalent generation CPU. Even in the favorable case for the CPU, where we just brute force loaded with kind of trivially parallel work to do, so it can do the optimal scheduling and hide everything. And except that it doesn't have factorization, use this code. Not beyond what GCC is capable of doing a bit automatically. And the other thing is it is basically easily adaptable to other models. Gesa talked about the basically first order Kuramoto model, which is also what was on the slides, and there's a second order Kuramoto model having a bit more state and such. We're using the same code for this. And other models could also be easily implemented. And the take-home message for you is if you have randomness on your GPU, try to sort it in a way that you can, along some direction which you can control, even if not a priori, but you can dynamically sort it. Especially in this case, it is simple because it's a static configuration for your graph. So you can basically take your time, sort it ideally, and then you run. So it doesn't cost a lot. Yeah, and also this will basically maximize the efficiency of memory accesses being adjacent to each other, even if you can't really control this, but just statistics in this sense, and it also improves load balance. I want to thank you for your attention.
Questions? There is one. Did you consider using an adaptive step size ODE integrator?
Yeah, I considered it because it's implemented in ODE-int. That's one reason also why I used ODE-int, kind of to, in the future, use this. But I didn't actually use it. It kind of would require changing like a few lines in the code to just, instead of the fixed-sized stepper, use the adaptive stepper from ODE-int, but it wasn't yet necessary. So we considered yes, but didn't do it, although it is not hard because the hard part is the differences, and we have this. It doesn't change.
Further questions? Does your data set fit on the GPU?
Yes. The Corning graph actually, 80 million links is not that large. In this one paper that Gesa referenced, there were random graphs with like 100 or 120 or 200 million links. That's kind of where it gets into the memory limit of the GPU. And then going multi-GPU with this is a hard problem because if the graph is random, you basically need to communicate all the graph. You don't have a boundary which you can easily define because the links are just going everywhere. In low-dimensional cases, like a random graph has like infinite dimension, so that's why you don't have a boundary. If the, or basically everything is a boundary, you don't have a bulk. In a low-dimensional case, you could do it, but like as I said, 200 million graphs you can run on a P100 or the larger one on the V100 with 32 gigabytes of memory. And as also because of machine learning is one reason, I mean, the HPC is demanding more memory on a GPU, and I think actually machine learning is pushing vendors to actually put it in, because they need large networks and they also want to have like all their weights on the GPU at the same time, because otherwise it's not efficient.
One more question. You are using flat buffers and not textures. Perhaps textures could provide more options for data locality organizations. Have you considered that?
Yeah, the thing I didn't look much into textures in many cases. The thing is, modern GPUs, I mean, some time back there was a lot of things you could do with textures, but now GPUs got L2 cache additionally, which kind of alleviates, as far as I read at least, much of the uses of texture caches. So all of the, actually we have pretty high cache hit rates, level 2 cache hit rates even, in this code, in the random graph, because sometimes they're just randomly already there. So basically it's already cached with the L2, and I guess the advantage of, in this case, using texture memory, especially since basically the memory you want to load is something that's basically just the whole GPU memory in the worst case. And having this texture cache versus just using normal L2 cache doesn't help, or it's maybe not even possible because you can't bind textures so large.
Thank you very much. Let's thank Jeffrey again.